So let's go ahead and start off with the topic of acids and bases. When we talk about acids and bases, so we define acids and bases by using the Bronsted-Lowry concept. What is the Bronsted-Lowry concept? The Bronsted-Lowry concept basically states that an acid can be defined as a substance that can donate a proton, right? So any substance that can donate a proton, that substance is going to be considered an acid. What do we mean by a proton? So a proton is going to be your hydrogen ion. Hydrogen ion is considered to be a proton, and any substance that can donate a proton will be known as an acid. And this is according to the Bronsted-Lowry concept. An alkali is a substance that can accept a proton, right? So it has to be able to accept a proton. So for a substance to be a proton acceptor, for a substance to be able to accept protons, it needs to have a lone pair of electrons that it can use to make a dative covalent bond. For example, we have the hydroxide ion. We know that the hydroxide ion has basically what? It has, it's a base, right? And it can accept a proton, it can take a proton, it can bind with a proton. So how does it do that? It has a lone pair of electrons. Because it has a lone pair of electrons, so it can make a dative bond with the hydrogen ion, or it can make a dative covalent bond with the proton, and that is how it is able to act as a proton acceptor. So according to the Bronsted-Lowry concept, acid is a substance that can donate protons, while alkali is a substance that can accept protons. Proton is your hydrogen ion, and for alkali to act as a proton acceptor, it needs to have a lone pair of electron that it can use to make a dative covalent bond. Now, when we go ahead and talk about it, there are certain substances that are known as amphoteric substances. What are amphoteric substances? Amphoteric substances are those substances that can act as an acid as well as a base. What do I mean by that? One of the substances that is considered to be amphoteric and is really common is water. If I react water with hydrochloric acid, water will act as a proton acceptor. It will act as a proton acceptor and it will accept the proton from hydrochloric acid and it will give us an ion known as H3O+. This is known as hydroxy ion. So it will form a hydroxy ion, which is going to be water, accepting one of the hydrogen or one of the protons from hydrochloric acid. The chlorine will then turn into a negative ion like this. So in this particular case, you can see water is acting as a base because it is acting as a proton acceptor. And if you're going to take a look, it has a lone pair of electrons, right? Over here, this oxygen has a lone pair of electron. And since it has a lone pair of electron, it is able to donate one of those electrons to the hydrogen ion and make a dative covalent bond. That's how you're getting your hydroxy ion. This is something you studied in your unit 1 and unit 2 when you did covalent bonding. Now, the same water can also act as a proton donor. It can act as an acid. So if I combine this with ammonia, for example, what will happen? The hydrogen will donate its, water will donate its hydrogen to the ammonia. Ammonia will turn into ammonium ion, NH4+, and your water is going to end up as OH-. Again, over here, your nitrogen has a lone pair of electrons, right? Because it has a lone pair of electrons, it is able to donate it to the hydrogen ion and make a NH4 plus. So that's what I said, that for it to be a proton acceptor, it needs to have a lone pair of electron that it can use to make a dative covalent bond. Now, over here we have another. So this is how water is acting both as an acid and an alkali. In the first equation, it is acting as an alkali by accepting the hydrogen ion. In the second equation, it is acting as an acid by donating the hydrogen ion. So those substances that can act both as acid and alkali, we consider them to be amphoteric substances. Now, over here, there is another terminology we have to know about: conjugate acid and base pair. As you can see over here, the equation I have made, this is a reversible equation, right? So when we talk about the forward equation, when we talk about our forward equation, so in the forward equation, our hydrochloric acid is acting as the acid, our water is acting as the base. Now, what about in the backwards reaction? In the backwards reaction, this hydroxyl ion is donating the hydrogen to chlorine and it is turning back into HCl, right? In the backward reaction, the hydroxyl ion is donating the hydrogen ion to chlorine, which is turning back into HCl, and hydroxyl ion is turning back into water. So in the backward reaction, hydroxyl ion is the one who is donating the hydrogen ion. So it is acting as the acid and it is donating the hydrogen ion to chlorine. Chlorine is accepting the hydrogen ion. It is acting as the base. And the reaction is going backwards and chlorine is turning back into HCl and hydroxyl ion is turning back into water. So over here, can you see that we have our over here, we have our HCl, right? So over here, the HCl is acting as an acid and over here it is acting as a base. So this is going to be considered to be one conjugate pair. This is one conjugate pair. With one conjugate pair. On the forward reaction, it is acting as an acid. On the backward reaction, it is acting as a base. So these are both of these, your hydrochloric acid and the chlorine ion, they are going to be considered one conjugate pair. And over here, water and hydroxyl ion. So water, on the forward reaction, water is acting as a base. But on the backward reaction, hydroxyl ion is acting as the acid. So this is our second conjugate pair. Similarly, let's take a look at the second equation. You will see similarly, we will have conjugate pairs over here as well. In the forward reaction, water is acting as the acid, right? And ammonia is acting as the base. In the backward reaction, ammonia is acting as the acid because it's donating the hydrogen back to OH, so it can turn back into water, and ammonium ion can turn back into ammonia. So NH4 is acting as the acid while your hydroxide is acting as the base. So your water in the forward reaction is acting as an acid. In the backwards reaction, it is acting as a base. So this is a conjugate pair. And ammonia in the forward reaction is acting as a base and in the backward reaction is acting as an acid. So this is another conjugate pair. Making sense?
Yes, miss.
Now, when we talk about it, there are acids that can only donate one proton, right? Like HCl. HCl can only give you one hydrogen ion. Or we can have nitric acid. Nitric acid will also give us one hydrogen ion, right? Those acids that can only donate one proton, we call them monoprotic or monobasic. Both terms are correct. We will call them a monoprotic acid or a monobasic acid. Those acids that can donate 2 hydrogen ions, for example, sulfur H2SO4. So those that can donate 2 hydrogen ions, those will be considered as diprotic or dibasic acids, right? So those acids that can donate 1 hydrogen ion are known as monoprotic or monobasic. Those that can donate 2 hydrogen ions, they are known as dibasic or diprotic. Carbonate ions can accept 2 protons. Hence, we call them diprotic or dibasic bases, right? So those that can accept 2 protons, those that can take 2 protons, those substances that can accept 2 protons, we call them diprotic bases or diphasic bases. Okay. Now, when we go ahead and we talk about it, so we have gone over our amphoteric substances. Now, what about nitric acid? Even though nitric acid is an acid, it can act as a base. Even though it is an acid, it can act as a base. And this happens in a very specific reaction, right? So basically, when we have our benzene, right? Benzene is a ring structure that we are going to cover when we do organic chemistry. So when we have our benzene and we want to nitrate it, right? We want to add nitrogen to it. So when we want to add nitrogen to it, we have to do a certain reaction, right? It is known as nitrating benzene. We are nitrating our benzene. So what do we do? How do we nitrate our benzene? So the entire process I'm not going into right now, but this is going to take place in this specific situation. In this specific situation, nitric acid will act as a base. So we take our sulfuric acid and we take our nitric acid. In this particular situation, nitric acid will act as a base and sulfuric acid will act as a acid. And you're going to end up getting 2 ions, HSO4 minus because hydrogen sulfate ion plus H2NO3 plus. That is, the nitric acid has accepted 1 hydrogen ion. And in this scenario, you can see in the forward reaction, sulfuric acid is acting as the acid, nitric acid is acting as the base. On the other hand, in the backwards reaction, sulfuric acid is acting as the base because in the backward reaction, our H2NO3 is donating hydrogen ions to hydrogen sulfate, so it can turn back into sulfuric acid. So hydrogen sulfate is acting as the base while this is acting as the acid. So this is going to be one conjugate base and this is going to be the other conjugate base. So this is one specific scenario in which nitric acid is going to be acting as a base. Now, we need to know about our definitions of strong acids, weak acids, strong alkalis and weak alkalis. A strong acid is an acid that will completely dissociate in an aqueous solution, right? Examples of strong acids are nitric acid, sulfuric acid, hydrochloric acid, phosphoric acids. All of these are considered to be strong acids. On the other hand, a weak acid is an acid that will only partially dissociate in an aqueous solution. So weak acids would include carboxylic acids, ethanoic acid, propanoic acid, carbonic acids. All of these are considered to be weak acid. So a strong acid is going to completely ionize in water. So, for example, if I have hydrochloric acid, it's going to completely dissociate, completely ionize to give me hydrogen ions. On the other hand, a weak acid is only going to partially dissociate, meaning that it is going to give me hydrogen ions and it's going to give me over here. This is methanoic acid. So methanoic acid is dissociating to give me hydrogen ions and methonate ions, right? So weak acids are a reversible reaction because they're only partially dissociating. So the hydrogen ions can combine back with the methonate ions and they can give back your methanoic acid. So this is a strong acid and a weak acid. A strong alkali and a weak alkali, same definition. A strong alkali is an alkali that will completely disassociate in an aqueous solution, while a weak alkali is an alkali that will only partially disassociate. Your group 1 alkali are all strong alkali. Sodium hydroxide, potassium hydroxide, lithium hydroxide, cesium hydroxide. These are all strong alkali. Weak alkali, for example, would include ammonia. Now, do you want to ask anything, Manu?
No, miss.
Okay. Now, there is a big question, and that is how we can actually measure the pH of the solution, right? How can we measure the pH? So measuring the pH is, of course, you're going to be using your, you can use a machine like a pH meter. We have to talk about how we can calculate the pH of a solution. So to calculate the pH of a solution, basically, when we are measuring the pH, we are measuring the hydrogen ion concentration, right? Think about it this way. A strong acid is going to have a high concentration of hydrogen ions. Since it's going to have a high concentration of hydrogen ions, what will happen? That since it's going to have a high concentration of hydrogen ions, so the pH we get is low. So for example, a strong acid will have a pH of 1 or a pH of 2, right? So the reason an acid will have a low pH is because it has high concentration of hydrogen ions, right? And when we talk about an alkali, so in an alkali, the concentration of hydrogen ions are very low. Since the concentration of hydrogen ions are very low, so the pH we get is very high. So pH is inversely proportional to the concentration of hydrogen ions, right? So when we're calculating the pH, we're actually measuring the hydrogen ion concentration. Now, when we talk about the formula for it, there are two formulas for it. Either we can use pH is equals to minus log of hydrogen concentration of hydrogen ions, right? Either we can do minus log and then concentration of the hydrogen ions, or we can do pH is equals to log 1 upon hydrogen, concentration of hydrogen ions. Both formulas are applicable and the concentration of hydrogen ions will be in mole per TM3. So either we can do 1 upon hydrogen ions and then take out the log to calculate the pH, or we can do minus log of the hydrogen ion concentration. Both formulas are correct. Both formulas are applicable. So for example, over here, the question is saying calculate the pH of aqueous solution of following monobasic strong acids. So for example, we have 0.001 mole DM cube HCl. So we can use the formula pH is equals to minus log H plus. The concentration of your hydrogen ions is 0.001. This is a monobasic acid. So the concentration of the hydrogen ions is going to be the same as the concentration of the acid, because the acid will only give you one hydrogen ion. So you will simply put this in the calculator and you will calculate your pH. Right? So this is how you're going to go ahead and do your calculations. Now, when we go ahead and we talk about it, you can say, okay, miss, this is easy for strong acids, because in strong acids, the acid will completely disassociate. So all of the concentration, whatever is the concentration of the acid, the concentration of the hydrogen ions will be the same because it's completely disassociating. What about in a weak acid? In a weak acid, the weak acid will only partially dissociate. So how are we going to get the concentration of hydrogen ions? Because the concentration of the acid will not be the same as the concentration of hydrogen ions, because the acid is not completely ionizing. So when we want to find out the pH of a of a of a of a of a weak acid, we have to find something that is known as acid dissociation constant, right? So we have to use the acid dissociation constant. So how can we calculate the acid dissociation constant? This is our weak acid, okay? I have my methanoic acid. My methanoic acid is partially ionizing. My methanoic acid is partially ionizing to give me hydrogen ions plus methonate ions. So I'm going to do product over reactant. My product is methonate ions. So I will write that down, right? And my other product is hydrogen ions. So I'm going to write that down. So that is the product. So concentration of my methonate ions multiplied by concentration of hydrogen ions divided by concentration of the product. The concentration of the product is the concentration of your methanoic acid. So when I put this formula, I will end up finding my acid dissociation constant. The symbol for acid dissociation constant is Ka. Okay. The formula is product over reactant. Your product is, you have your methonate ions, you have your hydrogen ions. So concentration of the methonate ions multiplied by concentration of the hydrogen ions divided by the acid. This would give me my acid dissociation constant. Right? So when we go ahead and we talk about it, we use this to, so we can use the acid dissociation constant to do our calculation. For example, look, this is the same scenario I was talking to you about. We have our methanoic acid, and since it's a weak acid, it will partially dissociate. So this is ethanoic acid, not methanoic acid. This is ethanoic acid. Ethanoic acid will partially dissociate to give you your ethonate ions and hydrogen ions. When we will make the expression for our constant, for our acid dissociation constant, the concentration of the product divided by concentration of the reactant. This will be the expression, right? Now, when we go ahead and we talk about it, we have to realize that the concentration of the negative ion and the concentration of the positive ion will be the same, right? I mean, think about it. The concentration of the positive ion and the concentration of the negative ion are going to be the same, right? That is why they will combine back with each other and they will again make ethanoic acid in the backwards reaction. So the concentration of the negative ion and the positive ion is exactly the same. So step number 1, I write down my expression for the dissociation constant. I write this down. After writing this down, I realize, oh wait, the concentration of the hydrogen ion and concentration of the negative ion will be the same. I mean, it makes sense. Imagine if your HCl was the one that was dissociating. So the amount of hydrogen and amount of chlorine would be the same. It's a 1:1 ratio. So the amount of hydrogen and the amount of ions, positive ions and negative ions are the same. So instead of writing it down as separately, we can write them both together. Since the concentration of both of them is the same, I can simply write it down as concentration of the hydrogen ions squared, right? For example, if the concentration of hydrogen ion was 0.1, the concentration of the negative ion would also be 0.1. So I could simply write down 0.1 square. It's the same thing. either I can write down 0.1 multiplied by 0.1 or 0.1 square. So either I can write down negative ion multiplied by positive ion, or I can simply write down hydrogen ion squared. And then the rest of the formula remains the same. Now, this is equal to your Ka, which is the dissociation constant. The dissociation constant has been given to us as 1.74 into 10 raised to power negative 5. Right? They've already provided to us. We need to find out the concentration of the hydrogen ion. The concentration of the acid is 0.05. So we have the acid in the denominator. So I will remove the acid and I will write down 0.05. So 1.74 multiplied by 10 raised to power negative 5 multiplied by 0.05 is equals to hydrogen ion squared, right? And then I'm going to get my answer, I will take out the under root. So hydrogen ions are going to come as 9.33 into 10 raised to power negative 4. So this is how you will get the concentration of the hydrogen ions for a weak acid. Now that you have the concentration, finding the pH is easy. Simply use the formula for pH. Minus log 9.33 into 10 raised to power negative 4. That's it. Once you have the hydrogen ion concentration, you apply the formula for pH and calculate the pH. The only thing you have to get is your hydrogen ion concentration. So for a strong acid, it is easy. We can simply get it from the concentration of the acid by looking at the mole ratio. But for a weak acid, it's not easy because it's only partially dissociating. So we need to use our dissociation constant to go ahead and calculate what our concentration of the hydrogen ion is, and then we can calculate the pH of the solution. Is this all making sense? Any confusion in any of this?
No, miss.
Okay. So now there is something known as pKa, right? pKa is basically when we take our dissociation constant and we take out the negative log of it. So if I have my dissociation constant and I take out the negative log of it, I will be able to calculate pKa. So pKa is simply the negative log of the acid dissociation constant. So generally speaking, two things you have to remember. Greater the value of the dissociation constant, the stronger the acid. The greater the value of dissociation constant, stronger your acid. But for pKa, it is the opposite. Greater the value of pKa or smaller the value of pKa, the stronger the acid. So pKa and the strength of the acid have an inverse relationship. But Ka and the strength of the acid have a direct relationship. So Ka and the strength of the acid have a direct relationship, while pKa and the strength of the acid have an inverse relationship. And to calculate pKa, we will take our acid dissociation constant and take out the negative log of it. Now, you can say, okay, miss, this was for a monobasic acid. Both of these are monobasic acid, miss. This one you told me for HCl, that was also a monobasic acid. And this one, your ethanoic acid, miss, this was also a monobasic acid. What if we have a dibasic acid? Right? What if we have an acid that is giving us 2 hydrogen ions? Then how are we going to solve it? So when we go ahead and we talk about it, we are now going to, how are we going to go ahead and do the calculation. One second. So, for example, when we talk about our sulfuric acid, right? So when we talk about our sulfuric acid is a very common dibasic acid. Now, when our sulfuric acid dissociates, this is the equation that you and I have studied. This is the overall equation. In reality, the acid breaks down or it dissociates in two steps. Okay? Step number one. Step number one is that it will first break down to give you one hydrogen ion and hydrogen sulfate ion, right? This is the first step. It's going to dissociate to give you hydrogen ion and hydrogen sulfate ion. This is the first the first step of it, right? This is going to be the first step of it. So the first step is that your sulfuric acid is going to break down to give you hydrogen ions and the hydrogen sulfate ion. Then this hydrogen sulfate ion continues to dissociate. It continues to break down and it gives you hydrogen ions plus sulfate ions. Now, over here, hydrogen sulfate ion is a weak acid. That is why the second step is a reversible reaction, because the hydrogen sulfate ion is a weak acid. So it's going to go ahead and dissociate partially. So this is how sulfuric acid is dissociating, right? When you're going to go ahead and talk about it, it is dissociating. Majority of the hydrogen ions are removed in the first step. The amount of hydrogen ions removed from the second step are quite small, they're negligible. But this is how your sulfuric acid is going to dissociate, right? Now, when we go ahead and talk about it, let's say that we have 0.5 mole dm cube of our sulfuric acid. So since we have 0.5 mole dm cube, so what did I tell you? Since the mole ratio is 1:1, so the concentration of hydrogen ion is also going to be 0.5 mole per dm cube, right? Now, what about the hydrogen ions that we are getting? So this is the first step. In the first step, it is easy, right? In the first step, it is easy because in the first step, it is basically going to be easy because we have a 1:1 ratio. And this is in the first equation, sulfuric acid is a strong acid. So the concentration of the acid is going to be equal to the concentration of the hydrogen ions, right? And hold on, just give me 1 minute. Now, the second step of the equation is basically where you have your hydrogen sulfate ion. I told you hydrogen sulfate ion is going to act as a weak acid. Now, I'm not going into details of calculations. You don't have to go ahead and do these calculations. The entire point is that if you do the calculations, you will see that from the second equation, the concentration of the hydrogen ion that will be calculated is going to be very, very low. And as a result, what is going to happen? That the contribution of the hydrogen ions from the second equation, from the hydrogen sulfate, that is negligible, right? So the majority of the hydrogen ions will be produced by the first equation. Majority of the hydrogen ions will be produced by the first equation, in which the concentration of the acid is going to be same as the concentration of the hydrogen ions produced. In the second step, the concentration of the hydrogen ions is negligible because majority of the hydrogen ions have already been produced from the first step of the dissociation. Now, we need to talk about something known as ionic product of water, right? So when we talk about water, our water can also dissociate to give us hydrogen ions and hydroxide ions. So if we go ahead and we take out the formula for the acid dissociation, right? The formula for acid dissociation would be product divided by reactant. This is your product and this is your reactant. Now, when we go ahead and talk about it, since when you talk about water, if water is constant at a given temperature, if water is going to be constant at a given temperature, so over here, this level of water, they're saying it is constant. If the level of water is constant or the concentration of water is constant, so we can remove it from the denominator, right? So we will be left with concentration of hydrogen ion multiplied by concentration of hydroxide ion. This is equal to Kw. What is Kw? Ionic product of water. The value of ionic product of water is fixed at 298 kelvins. That's new room temperature, right? So in room temperature, it is going to be fixed. It's going to be 1 into 10 raised to power negative 14, right? So the value of your ionic product of water is fixed. It is 1 into 10 raised to power negative 14, right? And when we talk about it, so water is a neutral compound, right? In that means that water is a neutral compound. So the concentration of the hydrogen ions and the concentration of the hydroxide ions are going to be the same, right? That's what I told you. They have a 1:1 ratio. So whatever is the concentration of the hydrogen ion, concentration of the hydroxide ion is the same. So we can write it down as hydrogen ion square is equals to Kw. Your Kw is 1 into 10 raised to power negative 14. So we can find out the concentration of the hydrogen ion by doing under root. So concentration of hydrogen ion is going to come out as 1 into 10 raised to power negative 7. And if you calculate the pH by using minus log, so you will see the pH you will get is 7, which is exactly proving what you and I know, that water is a neutral solution. Since water is a neutral solution, hydrogen and hydroxide ions are the same. So the formula for ionic product of water is hydrogen ion concentration multiplied by hydroxide ion concentration. And the value is fixed. It is 1 into 10 raised to power negative 14. And if we do the calculations, we will clearly see that water has a pH of 7 and it's a neutral solution. Now, what is pKw? Exactly the same as pKa. if I take the ionic product of water and I take out the negative log of it, so if I take out the negative log of it, I will end up getting my answer as pKw. So for example, they're saying, look at the question. Calculate pH at 298 Kelvin of an aqueous solution of sodium hydroxide of concentration 0.02 mole per dm cube. So we have potassium hydroxide, right? Potassium hydroxide is a strong alkali, so it will completely dissociate in water. So it's going to completely dissociate to give you potassium ions and hydroxide ions. So the concentration of the hydroxide ions is going to be the same as the concentration of the of the alkali, right? Concentration of the hydroxide ion is going to be the same as the concentration of the alkali because this is a strong acid. So you will say, okay, ma'am, since the potassium hydroxide is 0.02, so hydroxide ion must also be 0.02. But miss, how will we calculate the pH? The formula is for hydrogen ions, but over here we have hydroxide ions. This is where we will use ionic product of water. The formula for ionic product of water is hydrogen ions multiplied by concentration of hydroxide ions. Ionic product of water is 1 into 10 raised to power negative 14. We need to calculate the concentration of the hydrogen ions. The concentration of hydroxide ions is 0.02. So you calculate the concentration of hydrogen ions, that will come as 5 into 10 raised to power negative 13. And then you can use the formula pH minus log the concentration that you've just calculated, and you will end up getting your pH as 12.3. So this is how you can calculate the pH of an alkali. So if you take a look over here, as the formula of the base is changing, right? As the formula of the base is changing, the strength of the base is also increasing. It's getting stronger, right? Right? So when you go ahead and you talk about it, that is exactly what you can see. So as we are, so over here you can see that this had this was ammonia. Ammonia was a weak base. Sodium hydroxide on the other hand is going to be a stronger base. And over here, you can see that as the pH is increasing, the strength of the acid is decreasing, right? That's what you and I know, that higher the pH, the weaker the acid is going to be. And higher the pH, the stronger your alkali is going to be. So when we talk about our salts, right? When we talk about our salts, how will we know the pH of the salts? So please learn this table. If you have a strong acid and a strong base, right now we're going to do titrations. So when you're doing titration of a strong acid and a strong base, the salt that you will make is going to be a neutral salt and it will have a pH of 7. If we have a salt of a weak acid but a strong base, acid is weak but the base is strong, so the salt that will be made is going to have a pH of greater than 7. It's going to be an alkaline salt. Salt of a strong acid and a weak base. So if you have a strong acid, right, and your base is weak, in that situation, pH is going to be less than 7. And if both the acid and the base are weak, in that situation, we will take a look at our Ka. So dissociation constant of acid and dissociation constant of the base. If both of them are equal to each other, of both the weak acid and the weak base, both of them have the same dissociation constant, pH will be 7 of the salt. If it is going to be dissociation constant of the acid is greater than the dissociation constant of the base, it will be less than 7. It will be towards acidic. And if the dissociation constant of the acid is less than the dissociation constant of the base, it will be more than 7, right? So this is how you determine the pH of the salt. For example, now, what do I mean by this? We're going to do all of these curves, right? So you need to know this to be able to figure out the endpoint of the curve. For example, you're doing a reaction between hydrochloric acid and you're doing a reaction between your sodium hydroxide. Both of them are strong, right? This is a strong acid and this is a strong base. So your product, which will be NaCl, this NaCl is going to be a neutral salt. It will have a pH of 7. What about if you have a weak acid like ethanoic acid and then you have a strong base like sodium hydroxide? So in this situation, you will end up getting sodium ethonate as your salt and water. Now, over here, since we have a weak acid and a strong base, so the base is strong, meaning that the pH of the salt is going to be towards the base. Because the base is strong, so pH of the salt is going to be above 7. Now, what if we have a strong acid, but we have a weak base? So in this particular situation, you are going to end up with a salt of ammonium chloride. This salt, so the acid is stronger, so the salt is going to have a pH of less than 7. And finally, what if both of them are weak? What if the acid is weak and the base is weak? In that case, we will take a look at the dissociation constant. If the dissociation constant is for both of them is the same, pH will be neutral of the salt. If the acid has more, so the pH will be less than 7. If the base has a greater dissociation constant, the pH will be greater than 7. Okay. So this is how you are going to take a look at your salts, right? And this is exactly what you have to basically go ahead and remember. So this is really important because this will later on help you solve your titration curves, right? Now, let's take a look at this table. This is showing us concentration of the acid, right? Concentration of the acid. Over here, the concentration of the acid is, this is basically the concentration of the acid. So over here we have 1, then 0.1 mole per dm cube, 0.01 mole per dm cube, 0.001 mole per dm cube, 0.001 mole per dm cube, right? So as you can see, the concentration is basically changing. So as you can see, in each situation, the acid has been diluted, right? Over here, I have diluted my acid and I have further diluted the acid. Then I have further diluted the acid, right? So I'm going ahead and I am diluting my acid further and further and further and further, right? So what is going to happen that you will notice that the pH increases by a factor of 1 unit for each 10-fold decrease in concentration. I am decreasing the concentration by 10. I am diluting my solution by 10, or I'm decreasing my concentration of the acid by 10. The pH is increasing by factor of 1, right?
Yes, miss.
So as you can see, the acid is getting weaker and weaker and weaker. Eventually, you will end up reaching a point at which the concentration of acid is going to be so low that it is basically going to coed and it's going to be completely neutral. For example, if you decrease the concentration of the acid to 10 raised to power negative 8, at that point, the contribution of the hydrogen ions, the production of the hydrogen ions is going to be so low, then it is basically going to be close to neutral. The pH is going to be close to 7, right? So that is basically what happens, that as the concentration of the acid is going to decrease, the pH is going to increase. For a strong acid, this is the relationship. As the concentration decreases by 10, the value of pH increases by 1. For weak acid, again, we are decreasing it by the factor of 10. I am decreasing the concentration by the factor of 10. And as you can go ahead and see that the pH is increasing by the value of 0.5. So again, as the concentration is increasing, the pH is also increasing. It is going towards alkaline side. But it is not increasing as much as it was increasing for the acid. Okay, strong acid. In the strong acid, the change in the concentration produced a greater change in the pH value. For weak acid, the change in concentration is producing a less change in the or less increase in the value of the pH. Any confusion so far? Anything you want to ask regarding the topic? Is this all clear?
Yes, miss, it's clear.
Okay, now the next thing we have to basically go over in our topic is our acid basis solution titration, right? How we are going to make our titration correct. And we have to talk about our buffer and buffer solution. Mahanur, I think we should stop over here for today because this is the whole new topic. So I don't want to start it off right now. So we can go ahead and stop it over here for today. And in the next class, then we will pick off exactly from here and continue from where we left off. All right?
Okay, miss.
Okay.
Have a good day.
Thank you so much, Mahanur. See you in the next class. Have a good day.